Hello everyone. So in this video we're going to have this coupled oscillator discussion. The utility of the coupled oscillator is we actually get to solve for the eigenmodes and the eigenstate of, or the eigenmodes and the eigenvalues of a system. And we're going to define this coupled oscillator system where we essentially have two fixed walls in the left and in the right, and we have two masses with springs in between both the walls and the masses. So we have three springs total. And here, before we get started, you can kind of imagine two different modes of oscillation, two normal modes of oscillation. And what do you think those are? And so if you think about it, you can actually, it's pretty simple to imagine where an instance where I can perturb this system here, like push one of these masses toward the right, and what I get out of it is two likely outcomes, two possible outcomes. The first outcome is where you have an oscillating pattern where both of these masses are in fixed positions from one another. So this position here is fixed. And the masses are sort of oscillating to the left and to the right, so sort of back and forth with this fixed position x naught, if you will. So this position isn't changing, and you have both of these masses kind of going left and right. That's the first so-called mode of the system, which we're going to solve for, by the way. The second mode of this system, by the way, is rather than the masses sort of moving in phase with one another, they move out of phase. And so what happens in this case is that you can imagine the center point along the spring sort of fixed in position, so it's not moving whatsoever. And these masses sort of sandwich this spring here in the middle and then repel from one another, at an equal rate, so to speak. So it's kind of like you have these masses coming toward one another, right? And then away from one another, and so on and so forth. So you kind of get this mirroring oscillation between the two masses. So that's the second sort of, the second so-called mode or the state of this system. And we're going to solve for those two. And the two equations, like in the case of the simple harmonic oscillator that we're going to invoke to solve for these states, are Newton's second law and Hooke's law. So we have F equals ma, and we have F equals minus kx. And so in order to get started, we can define, or we have to define actually, the spring constants, obviously, because we have this k value, and we have to define our masses. But we're going to keep them arbitrary for now. This is not necessary. We're going to call this k, this spring constant k, just simply k. We're going to call them all k. And we're going to call the weight of the masses, we're just going to leave it as m. We're going to leave this as m, because it's not a problem. And of course, this direction here is positive. It's our x direction. And what we're going to define before we get into this is any displacement of this mass, toward the right, we're going to call x1. Or not to the right, just any displacement. We're just going to denote as x1. This just means the displacement of the first mass. And likewise for the second mass, we're going to call x2. This would help us set up the equations that we can ultimately solve the eigenstates for. So the first step, obviously, since we're talking about eigenmodes / eigenstates, eigenfunctions, all the same thing, is to set up our eigenequation. We have to have an eigenequation. And so this is how we get started. So we're going to get started with the mass on the left. So let's set up an equation for the mass on the left. So we're going to say mass on the left, we're going to set this up as the mass times d squared x1. So this is the displacement x1 of the first mass over d2 squared, right? So this is the acceleration of the first mass. So, typical Newton's law, second law. And that's going to be equal to this minus kx. But we have to be a little careful here. What is the net minus kx? What is the net spring force on this first mass? You have to note that we have two strings here. We have two springs, not strings. We have two springs, the left spring and the right spring. And I'm going to color code this so it's easier to track. The first spring here, we have k. We obviously have k on the right as well. We're going to color this orange. And we sort of have to keep track of this. And so if this mass were to be displaced a distance x1 to the right, what would be the restoring force? Well, we do know from the previous videos, we know that, if this is our positive direction, then if I displace this mass to the right, this particular, spring is going to pull it to the left. And so we have minus kx1, right? But of course, this isn't all, because we also have the contribution of this spring here. And so how do we define this? Well, you may be tempted to believe that, well, if this is the spring constant k, if I were to displace it x1 toward the right, then, well, this spring here is going to compress with this particular spring constant, and it's going to push this mass to the left, and thus we should have a minus k1x, right? Not k1x. So is this correct here? It turns out it's not. It's not exactly. Because of course, if I were to displace this toward the right, this mass also moves and effectively stretches the spring in the middle. And so the question is, exactly how much does this spring compress? Well, it's pretty simple. We just take the displacement x1 of the mass on the right, and we actually have to subtract the displacement of this mass as a result of this mass displacing toward the right. And so if this mass displaces an amount x2, when this mass displaces an amount x1, then the total compressive force on the spring applied to this mass is equal to, and this is, I'm going to write plus k times x2 minus x1. So we have this mass x2 displacing toward the right and sort of stretching this spring, if you will, and this sort of offsets the amount of x1 that is compressed on the spring. And so I hope this makes sense. And so if we look at the mass on the right, we apply a very similar line of argumentation. So, whoops. So we have, once again, the mass is equal to d2x2. In this case, we have now our second mass, and the displacement is x2. And what do we have here? Well, we have, if I were to displace this mass toward the right, and I'm going to color this, purple. That's too similar. I'm going to call this color here. So if I were to displace it toward the right, what contribution would this spring have to this mass? Well, of course, it's going to displace it on the left, and so toward the left, right? So we're going to call this minus kx2. And likewise, with this particular spring, for the exact same argument that we made here, in this case, we have minus k times, or I'm going to draw this orange once again, minus k times x2, or x2 minus x1, right? And so this is what we have now. These are our two equations, and we can rewrite these two. I'm going to rewrite the two just to make it a little neater. What do we have? Minus 2x kx1 plus kx2. And here we have minus 2 kx2 plus kx1. So we can rewrite this and simplify it as such. All right. Now, going back to one of the arguments that we made in the previous videos, you will note that I can rewrite this mass on the left as 2kx1 minus kx2. So I'm just getting this. All I'm essentially doing here is I'm multiplying this by minus 1, because I have here on the right omega squared times m times x1. And you can look at the previous videos to know, you know, where the heck I got this from. You know, we know that this particular relationship here is true. Omega here is our oscillation, effectively. This ultimately ends up being our angular frequency. And so this tells us how many times these masses oscillate per second. And in the case on the right, for the mass on the right, we have 2k x2 minus k x1 is equal to omega squared mx2. So obviously, you know, before we have this here, but in reality there was always a minus in this omega squared, and so all I did was I just multiplied both the left and the right hand side by -1. So we got this, and likewise with this equation here. And here what I'm going to do is I'm going to essentially organize this as a linear systems of equations. So we're going to have a sort of an algebraic or linear algebra form of the equation. So we're going to invoke linear algebra here a little bit because it helps us. So what are we going to do? Well, I'm going to rewrite this equation as follows. I'm going to have 2k here, and you're going to see how this works. I'm going to have minus k here, minus k here, and 2k here. And this is a matrix that I'm going to be multiplying by x1 and x2. Now, of course, this makes sense, because if I were to multiply 2k times x1 minus or plus minus k times x2, I'm going to end up with this equation here. Likewise, minus k times x1 minus, and 2k times x2, I am going to end up with this equation up here. So what do I have here on the right hand side? Once again, I'm just going to have 2 over omega squared times m is equal to x1, x2. Right? And so I just simply rewrote these two equations in this form down here below. And this is going to allow me to simply solve for the eigenvalues rather straightforwardly. So let's define our eigenvalues. Actually, one of the cool tricks that we can do here is we can actually substitute or divide the capital K over to the right hand side and effectively rewrite the equation as follows. I'm simply dividing the big K here. So I'm dividing both sides by 1 over k. So I'm multiplying this by 1 over k. And this allows me to get rid of all of the k's here. And I'm effectively left with all of these constants. Omega squared times m over k is equal to x1 over x, or not over, but x1, x2. Right? And so this is pretty neat because I can actually simply rewrite this, or I can just set this constant here. This is simply a constant. I can set that equal to lambda, and that would be my eigenvalue, right? And so now what I have here is a eigenequation. This is my finalized, simplified eigenequation, and that's very nice because I can now I'm free to solve for my eigenfunctions and my eigenvalues. Right? So I have here a times x, so this is like my vector x, is equal to lambda times the same value x, or the same vector x. And so this is an eigenequation here. Eigenequation. All right. Now, you should recall how to find the eigenvalues and the eigenmodes of a linear algebraic expression like this one, so an eigenequation like this one. And the way we do that is by solving the determinant of this eigenequation. So what is the determinant of this matrix? Well, in order to do this, we actually have to subtract the lambda, the eigenvalue, over to the left. And so what we have is 2 minus 1 minus 1, 2 lambda x1, x2 equals 0. So So if we want to take an eigenvalue, something has to be equal to 0. Or if we want to solve the determinant, sorry, we have to set something equal to 0. And of course, we can just like factor out this x1, x2, and what we're left with is effectively, and actually, this can be equal to 2 times an identity matrix, which would effectively allow us to write 2 minus lambda minus 1 minus 1, 2 minus lambda. Right? Because technically, when we're working with with actual matrices and vectors, these constants like these are technically a constant times an identity matrix. And so if I wanted to be very strict here, this would actually be equal to 2 times, or I can just write the identity in this form here. This would actually be equal to lambda, lambda, 0, 0, x1, x2, right? That's the only way this can work out, right? And so here, when I subtract these two, this matrix from this one, I'm left with this equation down here. And so thus far, I haven't really changed anything. So what I have written up here is identical to what I have written down here. So now we simply solve for the determinant. And so the determinant of this is simply 2 minus lambda times 2 minus lambda. So it's just this term times this term minus this term, or plus this term times this term. So if we have a, b, c, d of x1, x2 equaling 0, the determinant is none other than a times d, this is just a refresher, plus b times c is equal to 0. And so this is what we're doing here. So we have minus 1 is equal to 0. And so here we have our polynomial lambda squared minus 4 lambda plus 3 is equal to 0. And if we apply our quadratic formula, we will end up with lambda is equal to 2 times 1 plus or minus 1/2. So you can verify this if you wish. But ultimately, we have solved for our eigenvalues. So here we have our eigenvalues. We have 2 different eigenvalues. We have 2 different eigenvalues. So we have the eigenvalue, so we can still say like lambda 1, for example, where it's 2 times 1.5. So we have 3 over 2 times 2, so we have 6 over 2, that's 3, right? And then we have our second one, our second eigenvalue, where we have 1/2 times 2, which is simply 1. And if we want to find what frequency, what angular frequency that corresponds to, well, we have this expression up here. We know that lambda is equal to omega squared times m over k. So we simply know that for the first case, for the first eigenmode, we can call omega 1, we have 3 times k over m and the square root of that, right? We have that as our first eigenmode or eigenvalue. I like to call them eigenvalue. Technically, lambda is an eigenvalue, but many people consider this particular frequency the so-called eigenvalue. It's just more convenient. It makes more sense because this lambda, this equation here doesn't really tell us much. And likewise for lambda 2, we have nothing other than k over m. All right, so these are the rates of oscillation in radians per second of the 2 masses oscillating. And so you can note here, the first thing to note is that one of the oscillations are faster, this omega 1 is faster by a factor of the square root of 3. in comparison to the other oscillation. And you can imagine that this key here, omega 1, corresponds to the case where the masses are oscillating against one another, and omega 2 is the case where the masses are oscillating sort of in phase with one another. So it's a quite a fascinating example here. And of course, if we want to solve for the actual corresponding eigenvalues, well, if we start with lambda 1, or, you know, where lambda is equal to 3, we simply, well, I mean, we know how to do this, right? We can simply substitute this lambda 3 into this equation up here. So we have 2 minus 3, that gives us negative 1 everywhere. So we have essentially negative 1, negative 1, negative 1, and negative 1. We have x1, x2 is equal to 0. And so what we have effectively here is our x1 is equal to minus x2, right? So what we simply have to solve for this. So we have minus x1 minus x2 is equal to 0. Here I'm simply multiplying this, so I'm left with this term here. So our eigenfunction here, in this case x bar, we can say is proportional to 1 and minus 1. So this is x1 and this is x2. And likewise, for lambda 2 is equal to 1, we have, back, if we substitute this back into the original expression above, the eigenequation above, we have 1, minus 1, minus 1, and 1. And this is x1, x2 is equal to 0. And in this instance, we have x1 equaling x2. And so here we have the case where the eigenfunction is proportional to 1 and, or not 1 and minus 1, but just 1 and 1. Where this is x1 and this is x2. And so this is interesting. You can see here that in the case of lambda 1, and recall that omega 1 was equal to the square root of 3k over m. So this is the faster oscillation. This plus and minus 1, this plus 1 and minus 1 corresponds to the masses oscillating opposite to one another. That's why you have this 1 and minus 1 here. And in the case of lambda 2, where you have the slower oscillation, k over m, these values are the same. So x1 and x2 are the same. And so as x1 is displaced, whatever distance x1, x2 is displaced by the exact same distance. Right, so we have this oscillation where the masses are fixed, like are in phase with one another, and they're essentially, the distance between the two are essentially fixed. And so this here concludes the mass on the spring problem. I hope it makes sense. We have solved for the eigenvalues here and here, and we have solved for the eigenfunctions, which is here and here. And in the next video, we're going to be discussing Hermitian matrices and operators.